Okay, so today I finish a proof of Poincaré conjecture based on what I said before. And first I summarized a bit, summarize what we did before. I didn't write down all the properties, but I just write down the properties we need today. So in the last few lectures, sometimes I give details, sometimes I outline. I basically construct the Ricci flow with surgery. Okay, so this means I have giving a three manifold. I pick up initial metric with certain normalization, namely you assume curvature big equal to -1, and the volume is of unit ball is big equal to half of Euclidean volume. So then you know there's a solution to Ricci flow with surgery. So more precisely, then what we have is we have a sequence of times going to infinity as Ti, okay, and it has a low accumulation point in any finite interval, and then I have a sequence of manifolds, and each time I passing these moments, the manifold we have a surgery for manifolds. So the previous manifold, the manifold before this Ti plus 1 is a manifold of Ti plus 1 plus a connection with these simple manifolds. Okay, so this is M1 copies of this and M2 copies of RP3. So maybe I put a bracket here, and then there are also a few space forms with all this gamma finite group. On each of these subintervals, we have a standard Ricci flow. Okay, so with standard Ricci flow, and initially this is, of course, now this metric at each t, so I is from 0 up. Okay, so at each of the Ti plus 1, of course, there is also some relation of a previous metric to a metric at that moment. So this was specified in the surgery process I did last time, but that since that it's a bit technical to write to phrase that precisely. But the only thing I needed here is I know there is basically there's a shrinking map, distance decreasing map. Okay, so from here, this is not a homomorphism because the manifold experience a surgery here, but we can crush these components, so we can make this map as a decreasing map, and also we can even make this map to be almost like degree 1 in a sense. Okay, to at least so maybe this is not quite correct. So maybe I should say should be any component of this. So there is a degree 1. Maybe I write this way. So for any component, because okay, so any connect component of how do I say? So maybe I put alpha here. So those are okay. So maybe AB, A, and MI plus 1 B. Okay, it's such that this phi AB T. Okay, so those stands for components of that. The component because MI, even you start with a simply connected one, after surgeries it may become disconnected. So this is a GI So what I wrote before, so this is gt and gti plus 1. Okay, t is between t is between here, where the t is between ti plus 1. Okay. And those stand for connected components. Okay. And this can be a degree 1. Okay. So today I want to, on the basis of this, I want to prove Poincaré conjecture. So what I want to do is, so I assume, so M is simply connected. You start with is simply connected. Then at least we know more. Namely, we know those will not appear at all. Okay, so each time you basically I also here I have to be careful here because it's connect sum of components here. Okay, connect sum. So this is maybe I put that's a little bit hard to write. So this is certain, it's connect components of B here. Okay, to be precise. Okay. So and for each A, B standard components. Okay. Maybe I put this way. So this is a disjoint. So I don't want to disjoint. And those are connected. Okay. So then you. So then each time, so this will become all this, just become. So those are gone. So that means mi. So each time mi of each component of is equal to disjoint of some mi plus 1, maybe b1 to mi plus 1 ba. Okay, so basically I want to prove each of these will become a differentiable sphere. Okay, so how we do that? We use this width we defined before at the beginning, but now I remind you what is this. Okay. So first factor, we know pi 2 of a space of loops and with a base point. So this is the same as pi 3 of M3. Okay. And this is not 0. This is not 0. Okay. So we pick up a C here. Okay. The first thing we observed is this is so first thing I observed, there is a CT, continuous family of CT, such that it's so it's non-trivial, and such that this homology class CT is the same as CTI for T in Ti, just some topological consequence. Okay, and C of this phi T star. Okay. So let me just put phi here. Okay, phi of this. So phi T of star of maybe I just put phi star of CT is CTI plus 1. Okay. So okay. So namely, I can find this, and this is and not 0 either. Okay. So you have what we do here is if I look at the surgery, so I start with say 3 manifold. Okay, and that's a 3 manifold. So then after a certain time, this is t equal to 0. After a certain time, I may have split into components. So this is say m at t equal to t1. Okay, so so you may also go on. So you may split further components, maybe, and this one may split into. Okay, so at t equal to t2 and so on. So what I'm doing here is I pick some class here. So I can I drop the a and the b, but it's you think it's the sum of a and the b. I can go pick up a component. I can, for example, go this one. So I start from c t here, 0 here. Okay. So then this goes to c t1. Okay. c t1, and then maybe it goes to depend. Then this splits with further components. I can go to c. You can also pick up that component. Depends. You choose. Okay. T2, so on. So only thing I want is I just topologically I pick up a sequence of class, so that maybe unless empty ti plus 1 is empty, is okay. Of course, if it's empty, I cannot do this. Otherwise, it's always there's a component because it's a degree 1 map, so I can keep doing this. So this way, I have basically I pick up a constant class here, which I pick. So I fix this. This is some just simple topological consideration. So I pick up these classes, then we define following things. So if it's not 0, we define so for any gamma, for any loop inside of this loop space, define A gamma to be the area, the minimizing area of Fd. So where F is any map from a D into your manifold, and the boundary goes to a gamma. So you take an infimum of area. Okay. So let's put it this way. So it's area okay. So I take an infimum of area here. So now I define for C, for define a W C of T. Okay, CT is equal to infimum of all the possible maps, such that this map is from S2 family into loop space, and the homotopy class of this is given by things, okay, C, and given by CT, okay, or now it's just simply C, okay. So without confusion, I will drop T here, and then the supreme for all the C inside S2. So for all the C inside S2, gamma C become a loop, so I compute the gamma C here, gamma C here, okay, gamma. So I defined it before. So what we want to prove is the following. Okay. Maybe I. So the key estimate okay. So this imply so d cos c dw ct dt. So this is always big equal to 0. Okay. And one level. So here, and the assumption if here, of course, I assume if MT is not empty, okay, it's not empty at that moment, okay. So I have this. This is less equal to this minus 2 pi minus half of R min T. So that's a scalar curvature of a metric GT and W cos CT. So I will derive this estimate here. So that's things I want to prove here. And in fact, I cannot give you all the details because this is in the full details where you can find the full details in chapter 18 in our book, and which like 80 pages. So following approach suggested by Paramount and which very sketch. Okay. So now let me first, assuming this, see, we can derive a Poincaré conjecture there, because these things tells us the following. Maybe I simply write down because of time has changed. So now you solve this equation, the corollary. Okay. The corollary, if m okay, so if MT, so let's make a convention here. So maybe then easy for me to say. If MT is just MI for T in a TI plus 1. Okay. So if MT is not empty, then so this is the case. Okay. So then what we have is the following. So then the W of this W cos CT is less equal to, let me write down solution. So W cos C at 0, okay, and 4T so plus twice pi of 4T plus 1 called the proof is very easy because if MT is not empty, of course all the previous MTI was not empty, so we have this differential inequality. On the other hand, this side is just so right hand side is simply the solution of the following differentiable equations of dw dt minus 2 pi and plus 1 plus 4t of w with the initial value w0 equal to 0. Okay. So on the other hand, this is because of a condition here, because of this for this solution of Ricci flow with surgery, we always have this estimate for low bound of scalar curvature. So this side, so this is simply less equal to minus 2 pi of minus plus 3. T. So whenever this differential inequality exists, namely whenever empty is not empty, so then you just use the ODE comparison theorem. Okay, so because this is simply the solution of this. Okay. So now, if you look at this corollary, because this is a leading term, and it's negative. So as t, when the t is sufficiently big, this dominates other two terms. So it becomes negative. On the other hand, I know this is whenever this is defined, this is non-negative. So that implies MT is empty for t sufficiently large. So then we are done. And I should say, when I do this, I pick up one chain of things, but you can pick up any of these possible things. Okay? So then you will prove eventually any component is trivial. Okay? If this is trivial, you can throw them out. You look at other components. Okay? So that's give you this. So the whole thing I need to do is to prove this inequality here. Okay. So how do we prove this inequality? Okay. So to prove this inequality, I first make a further reduction. So I make a notation here. So So I will. So in the following, I will say let W A T0 of T be the solution of ODE of dW dt equal to a minus 2 pi minus half. And the W at T0 is given by A. Okay? So sometimes I simply drop. Sometimes if for simplicity I will drop this initial time. I mean this subscript here, just for simplicity. Okay? So sometimes I may drop that. So now let me state another proposition, which is so actually now it's I manage to Ricci flow. Okay, so maybe before this I should say a little bit, because I somehow forgot to say, because this is only defined for Ricci flow. So this proof here, you can only do that when the Ricci flow is real Ricci flow. So I should add a remark here. So here we used or in this argument we also used the following things. If it follows from definition, we also used, so which I used the fact. Okay, so if so this W Ti plus 1 is always less equal to T equals to Ti plus 1. And the reason for that, because of this distance decreasing properties. Distance decreasing tells you the area will be decreased when you compute the area of in terms of this metric is smaller than area of this metric, maybe up to this like perturbation term. Okay. So you have you don't need to. So you have this inequality here. So you only need to do this. So we only need to prove to prove inequality, the differential inequality. In each in Ti plus. And also this W as defined is a continuous function. So we only need to do this. So the proof, even if we did surgery, because of if we understand because we have this property phi, so we don't need to really worry about the surgery time. Okay. So this is the things we assume. So here is a proposition we want to prove. Maybe I list here. So I list another proposition which is weaker than that, but implies that. So now I assume this is M. GT is a regular Ricci flow, as we said in let's say T0. Maybe I shouldn't say T0 now. So we say A less alpha less than B, beta. Okay, this interval. Okay. Or maybe I put the T0 bar to T1 bar. Okay. So it's a Ricci flow. It's a regular Ricci flow. So manifold is on a 3 manifold. Okay, M could be any of one of these manifolds over there. Okay, so fix the gamma from S2 to M, and any positive number to C. Okay. So one I say is there is a different family. There's always here is a continuous family. Okay, so from S2 to the space of loops. So I actually want this T. So T is between. So I have a family of loops. Okay, family of loops. So it's family of loops such that of course homotopy class of this is the same as a homotopy class of these. So this is the first thing. Second thing is for any C in the S2, this A area of gamma quota T0 bar C minus A gamma C is less. So namely, initially, this is approximation of gamma in the sense of area, and one of the following holds. So one is the length of this the ending T1 is small. Okay. Maybe I put this way. So with and such that. Okay. So So this is either very small or this A of gamma tilde T1 of C is less equal to W A gamma tilde T0 bar C. Okay, I dropped the T0 bar, so indicate that this is always the initial value there, okay, of T1 bar plus. So now, the first thing I want to just tell you, this is the proposition. In fact, soon I don't need this anymore, okay? I only think. So we'll imply the key estimate. Okay. So why is that? Let me tell you why this is true. Okay, so let's make a. So let's call this a star. Okay. So let me put the W, small w t, without any index, just the W of things with new initial data, C of T0 bar, okay, at T. Okay, it's a solution of that equation with these new initial values, okay, at T0 bar. So let's distinguish two cases. So case 1, okay, so case 1 is a W. So case WT1 bar is non-negative. Basically, we actually later on we will prove this is the only cases. So in this case, so we can do the following. Choose a very small eta for any etas positive small. Okay. So you choose C less than this, such that any loop gamma in the M in your manifold. Okay, so M is one of these MT here. So I will check M is this time is at some MT. Okay, at some MT. Okay, to prove this inequality. Maybe I can erase this now because I don't really need this anymore. Okay, so just or maybe later. So don't. I think I erased this so that you have can more focus on this part. So this W. This is original definition at this. I want to prove this differential inequalities, assuming that proposition.
So it depends on the design. But the other W depends on the real number? Or?
This is a real number. This is also a real number.
So what is the other W? The one in the middle?
This is small w. So this one is maybe I write this a little bit confused. So this one means is a solution of that ordinary differential equation over there, with this in the subscript as the initial value. Okay, at the initial moment. Okay, yeah. Okay, it's too many w's because and yeah. Sometimes if I don't do precisely, then you got confused anyway. So it's never. I don't know which is right. But anyway, so any loop in that with a length less than c bounds a disk. So why I always say a bounds a disk always means generalized disk. That means it's an image of map from the disk with area. That's always possible, right? So I mean, if the circle is so short, you can basically within some neighborhood. So once I have this, so other things I know is I'm sorry. So I chose this such that this is 1, and the 2. The 2 is what? Because this solution, this ODE clearly is depends on initial data continuously. So we can have a following for every A inside of 0. Maybe I don't need to do this, but anyway, so let's C of T0 bar plus things. The A of T1, T is less equal to W. Maybe half of that. This is just so I give you partly very precise. So now let's for simplicity. So this is easy to get. Okay. So suppose now I have this. So I have this family. So now this time this is family is chosen with respect to somehow like Ada here. Okay. So we have this family, and so now we take gamma. By definition, take gamma such that such that the supreme of A gamma C is C in the S2 is less equal to W C of T0 bar plus C. That's by definition. Okay. So that implies this is that implies by our choice. So that implies A of gamma tilde of T0 bar of C for any C. Okay, this is less than A of less than W C of T0 bar plus twice of this. Okay, so I guess it's sorry, not jump here. So maybe this is okay, and this is definitely okay. So let's do this C, okay, and one of that holds. So let's just be short. Okay. So let me erase this now. So maybe I jump the proof here. So then for any C, so we have two cases. So one case, in the first case, so let me just write quickly here. So in the first case, that means the area of a gamma. In the first case, that means the area of So in the first case, that means area of this, C, is less equal to eta by assumption, okay? By choice of that, okay? In the second case, so it's depend. So these cases may vary depending on which C you use, okay? So for some C, maybe first the case one, first property holds or the second property holds. So second case, I have this A gamma of T1 bar of C. This is less equal to, by the definition, by the choice. So this is W, okay, so it's WT plus 2 of this. So why is 2 of this? Plus eta. Plus eta. Why? Because I know, first I have this differential inequality here. Okay, I have these things here, but with this initial data, and this one is less equal to eta over 2. And however, this initial value for the ODE solution is in this region here. So I have this inequality. So you put them together, you get this. But now since the WT is bigger to 0, this is WT 1 bar. So since this is bigger to 0, so in either cases this is true. Okay, so this is always true. So this is always true. So this in fact is always true for any C. So now if this is always true, so case 2, so I want to say case 2, so WT, so I want to say a T1 bar less than 0. This is not possible. I want to prove this is not possible. If this is not possible, we proved these things. And this is for any eta. So we can take eta goes to 0. So then I proved this inequality for any C here. But that's exactly for any C. And the way I choose here, this any C, this one is approximate this. And this one is by choice is very close to this. So then, if this is ruled out, this is not possible. Then what I get, I will be able to prove. So then I will be able to prove this W, right? Which way? And I guess something here is I wrote is not quite. I want to prove this from above. T W T. Okay. So then what I proved. So if this is not possible, only case 1. So then I prove W C T1 bar. Okay. So this is because this is infimum. This will be always less equal to this W C T0 bar, and plus this. I'm sorry. This proved this W of T1 bar. Okay. But remember, this is obtained by OD as a solution OD with this initial value. So then differentiate this. On a T1 bar, and as T1 bar goes to T0 bar, we get the key estimate. Okay. So it's done. So only thing I need to rule out this. I need to rule out this. How do I rule out this? Maybe I just say quickly now, because this argument is not difficulty. Because basically you can think, if a T1 bar is negative, that by here I know this is very small. So let me just put this way. So then this is very small. This is very small. If it's either negative or very small. So either of these cases, that means either the area is small or length is small. So that implies this is trivial. The whole family is trivial, but you assume this gamma represents a non-trivial class. Okay. You understand what I say here? For any C, either here this is small, then area is small anyway. And here, if it's small, then area is small anyway. So that implies any loops in your family is trivial loop. I mean, bounds a trivial thing. So whole family will be trivial. Okay. So that's not possible. So this not possible because this will imply C is there. That's not possible. Okay, so maybe so you only have this case. You don't need to worry about this. Okay. So now we need to prove this. So now proof this is reduced to prove this, but proof is a bit tricky here. So first, let me try to prove it under certain assumptions. Okay. So what's the key point here? Key point here, for any gamma, basically you can think this is as the initial value. You can take this to be this. So then you need to produce this family along the Ricci flow. How do you produce this family? Okay. So the thing is to put the point to use the mean curvature flow. Okay. So let's consider mean curvature flow. So recall the curve shortening flow. So this is given as follows. So I consider C to be a map from say S1 across some interval, say T0, T from T maybe T prime, okay, into your manifold, and such that so satisfy the C of dt equal to h, the mean curvature at the xt, where the mean curvature is computed in terms of so it's slightly different from ordinary mean curvature flow. It's a mean curvature adapt to a Ricci flow in terms of gt at the moment t. So mean curvature is computed in terms of changing metrics. So, however, this flow is not much different from standard mean curvature flow, because the ambient curvature stay bounded anyway, because we assume there's good family of we only consider things in the good family of Ricci flow. And since ambient space are anywhere bounded, so this issue is not about. I mean, when you study this flow, we're more worried about whether this flow has whether the curvature of this flow stays bounded. So there's a fact is for this T prime, either the solution C solution C can extend across t prime, or so this is very similar. If I look at the curvature of this, t prime minus 0 is close up. So this criterion is same as before. So this seems to be typical in the charge. So now I want to prove that things. First, let's make life simpler. So let's now assume, of course, this assumption is not checked. Let's assume first there is a mean curve for any gamma, for any given gamma, say at least a smooth, say gamma, say this gamma, these things, okay, sufficiently smooth, giving. Because in general, the family could be just a continuous family, but we can always approximate the continuous one by smooth one, so that we can solve this mean curvature flow. There is a global solution. This is a global solution. So I should say for any loop, okay, good loop, in most loop, maybe I put this way, any in most. Gamma. So there is a global solution, C, X, T. So T is between such that with C, X, T, 0 bar equal to gamma. I suppose I have this. Let me derive that proposition. Okay. So basically, what I do here is, in order to derive the proposition, what I do is I take a gamma to be any of these curve here, or more precisely, I get this curve here. Okay. So then I want to construct the family for this particular C here. Okay. C. So. So let's prove this proposition and these conditions. So let's now quickly give you an idea. So proof of a proposition and these assumptions. See, that is a double star here. Okay. So then this time, gamma tilde t of C is simply the solution of a mean curvature flow, the flow, curve shortening flow with initial value gamma C tilde. Okay. So now we just pretend this time this I just take this to be a C and maybe too many C here. So this is so let's just assume this here. Okay. So maybe I put a bracket. So I guess a little bit crossing using for notations. So what I do here is so let AT being be be the minimizing area of the disk span CT. So CT is a solution here. Okay, let's follow notation here now. So first variational formula is the following. So we take the D, compute the area. So that's of dt. Okay. So this is less equal to this D. Say at any point t equal t prime. Okay, at t tilde say, and the area of phi p of this, okay, at t equal to t tilde. So where phi t is a family of phi t is a family of diffeomorphisms, say from M to itself, okay, is identity at t tilde, and preserve. So phi t on the boundary is just the C. So it's just consider variation, right? Variation. So this is so you have a family of curves C, which is deformed. So you simply extend this as a family of deformations. Okay. So it's family of maps. Okay. So then you compute this. So maybe I put this way. So then you compute this. It has this is by comparison. By comparison, because area of this is always corresponding minimizing area. So now this has two contributions. This is what I'm doing here is just first variational formula, but this time I have two contributions. One contribution from a changing of a matrix. Other one is just standard first variations, just the mean curvature comes out. Okay. So when you do this, you get things is the following. You take phi t tilde. So let's see. I shouldn't say this identity is just that standard disk. So it's a minimizing disk thing. So it's a minimizing. So this minimizing. Okay. So that means A. Maybe I put it this way. So A of t tilde is equal to area of phi t tilde of D. Okay. So let's pretend the disk to be embedded. If you have a branch point, then actually inequality goes well. It goes better in the following computations. Okay. So this is you have a phi t tilde of D. So then the change of a metric is given by minus of a Ricci curvature, of a trace of Ricci curvature in the tangential part. Tangential means tangential to disks. Okay, because this is compute as a time derivative of a volume form, induced volume from this. So that is the trace in the disk directions, and plus a contribution from so then you have a divergence of d phi dt, of course also at the t tilde. Okay. So now this one has two terms. One is a contribution of actually previous I have, so I can reduce this because mean curvature is 0. Okay. So now I use a divergence formula. First, I use a Gauss-Ballet theorem. Gauss equations. You can maybe I just do it quickly now. So this term you can rewrite as the following: use a Gauss equation, you can write this phi t tilde of d, and Gauss curvature of that, Gauss curvature of this disk, and minus half of a square, the second fundamental form, plus the scalar curvature ambient space. So this is use a Gauss equation, you can get this. So then for second term here, you use integrating by parts. That is, you exactly get minus the dependent sign of things. Okay. Sign. So this is just the boundary of t tilde of things at the geodesic curvature. That I use the mean curvature flow, because on the boundary it is given by a curve shortening flow. Okay. So then you look at normal components of this, give you a geodesic curvature of a curve. So this one, now this combines that, use the Gauss-Borel theorem. I think it's a plus here. So it depends on how you say a sign here. Anyway, so it's you will get this. So then this combines that, use Gauss-Borel theorem. That's minus 2 pi. Okay. And this one I dropped out, so this is less equal to that. Okay. So because this is Euler number 2 pi times Euler number of disk. So this one drop out, and I get minus R mean of half of that at the time t tilde, and then area of phi t tilde d. Okay. So this is exactly what we get here. This is exactly, namely, this dAt is less equal to minus 2 pi minus half of R mean of t of AT. So this okay, at t tilde thing. So now you differentiate this, you will get this inequality here. You don't need even worry about first case. It's always true second case. Okay. So yes? Pardon? Oh, okay. Sorry. So now, and these assumptions, we have a proof of this. Okay, proof of this. But now, why this is true? This is not true, so we have to make up this. So what he tried to do is basically, again, he tried to define weak solution of this, but actually weaker than a weak solution in a sense. So let's collect a few basic properties of a mean curvature flow, and then I tell you roughly how he get around this assumption. So a few facts about things. So when you get the geometric flow, what you do, first thing you do, and I guess most people can do, almost all the people can do, is you differentiate the evolution equation of curvature. Okay, so evolution of equation of curvature, you will get the following two things, like in the curve case. So to save time, so I'm not going to write down equation. So there are two quantities you know you can here. So facts about the mean curvature flow and curve shortening flow. Okay. So first, if you take LT to be whenever the flow exists, if you take a length of that of C of xt, okay, and let's say you also compute the total curvature of this. So this one, so then what you can do is, you know, then dl dt is controlled by, is less equal to some constant, c2 minus k squared. Okay, maybe I just, this is arc length. Okay, so let's see. Okay, and the d theta dt is less equal to c2. c2 is some constant, theta. Okay. So you know, if initially, so that implies this, since L is, so first imply L of t prime of t, any t is bounded by some L at t0 bar initially, and exponential of maybe c2 of t minus t0 bar. Okay, and theta 2. Okay. So you have this. Whenever the flow exists, this is true for any dimensions. Okay. So what how you prove it? As I said, you simply differentiate the equation again and derive an evolution equation on the curvatures, and then play some. Manipulate a bit. Okay. So if you assume, initial the length certainly is finite. You need to choose the initial. That's why I say I need to do some perturbation so that the total curvature at initial is bounded. It's not uniform bound, but at least it's bounded. Then you can bound it afterwards. Okay. So, and also you get, when you integrate this, you will get from 0 to t tilde, whenever it's a zig, dt, and the L2 long of curvature is uniformly bounded because by length. So let's put C3 here. Okay. So you have this uniform bound. So this bound may depend on the initial length. Okay, initial length. So you have these things. Of course, this not suffice to have this, because here basically I want this is your k, the norm here, and this is not enough because this is we need L infinity bound. Why we only have at most L2 bound in a sense. So what we do? There's a little trick. It's basically this trick is seems to be works well in every cases. Appears in every cases actually we have a global solution. So there are certain things. So we can put a ramp here. So ramp solutions. Okay, so what we do is here, let C, giving any C curve, giving any gamma, okay, curve from S1 into your M. So let's define the gamma lambda from S1 into M cross S1 lambda. So S1 lambda means the circle with a length 2 pi lambda, or lambda simply. Okay, it doesn't really matter. So this is, you can extend as x here, just goes to gamma x and the lambda x. So this one has a property, simple property. Look at the dot here, and the pairing with the u. U is the unit vector in circle directions. You fix some orientation, okay, the positive unit vector. So this is positive. This is positive. Okay, the way you define that. So let's pause this to be a function. This. So now with the given initial data instead of solving a mean curvature flow equation in the original manifold, let's solve this. Let's solve this. Solve d of c lambda dt equal part lambda here means that goes to here, and the mean curvature again, so mean curvature flow, so of c lambda t, and the ct of that initial value is given by gamma lambda. So you can define a corresponding function u, which is again is still this. So lambda here. So c lambda prime of u. It turns out that by maximum principle, maybe I just copy down the things. It's always a simple computation. So then the direct computation shows the following. First, is for some constant c prime dt of c prime t of u is bigger equal to double prime. So c prime t u, I guess, increases. Minimum increases at least. Okay, so maybe I said minimum increases. C prime t u increases. So that means initially, if this is positive all the time. So then you can talk about these things. So then you can make things, you can make sense of total curvature over u. Now this makes sense now because u is positive. So this will be bounded by k of u. So I just write down. So 2u prime of u of k of u prime plus c, some constant. C prime is some constant again. Maybe different from that c prime. So that by maximum principle tells you this is bounded. So curvature is bounded. And that implies for any lambda positive, this one has a global solution. So let's say, I guess this c lambda exists. Okay. So you have this. So what you want to do is next. So how do I produce that family there now? Is following. Okay. So then what I can do is I want to do start from in a proof of to do a following thing. So giving say a proof of proposition or outline proof of proposition. Okay. So giving a gamma from S2 to this, in the first state, approximate, find approximation. Okay. So find the approximation. This gamma tilde. Okay. So gamma tilde is again is from S2 to this, which we are use this as gamma tilde of T0 bar, such that total curvature is bounded. So it's smooth approximation such that total curvature is bounded. So total curvature of for gamma tilde of C is uniform bounded. I guess I should this time use B now, I guess, in the, okay, and S2. So we find the smooth approximation. So that's trivial to do. You just, okay. Of course, this constant here may depend on approximation. So this may depend on approximation. Okay. So then you step 2. You make these things, gamma tilde lambda, which is exactly produced that way. So this is just defined to be a base. This is a curve, and this is lambda. Okay. Lambda. Okay. So now you solve for any lambda. You solve the mean curve shortening flow to get f lambda tilde of T B for T okay, and initially this is given by this, okay, with gamma lambda T0 bar of B is just this. So we want to prove this P1 of gamma lambda tilde, okay, of T is the needed family. For when the lambda is so small. Okay. So small. P1 is a projection. P1 is projection to M, where P1 is a projection to M. P1 is a projection to M. So, guess my time is okay. Still have a few minutes, so 10 minutes. So now, so here actually comes two major technical parts. So we need to prove this, and so of course, when the lambda goes to 0, in a sense, this goes to a family. Whenever you can prove a convergence. So at least for initial curve, as the lambda goes to 0, you back to original curve. So we need to prove this family converge. Okay, family converge. So here is a few basic estimates we need, and so let me write down then. So it's a bit hard for me to do that. Okay. So first thing we do, so in order to prove this, first thing we do is the following. So I claim 1, okay, step 3, which I just write down this now. Okay. So they are constant. See, all these are constant. May depend on this initial value here, but it's independent of t here. So they are constant. So such that this A of area of this, the P of gamma tilde lambda T double prime of B for any B here minus A of P of P1, lambda tilde T prime of B, that's equal to C. So this is a uniform independent of B and C4 of T double prime. It may depend on this initial approximation, may depend on this constant here, but that's okay. Okay. So I have this. So this you can think how we get this is basically you can, if you compute the derivative of this, again it contains two parts. One part is a variation of ambient curvature, ambient metric. Of course, ambient metric is controlled, so it's certainly the derivative are bounded. There's another term which you can use a comparison. Say it's a derivative of this modulo this contribution of matrix, variation of matrix is a contribution. You can say it's other terms dominated by variation of this flow, a variation of this flow here, which is given by mean curvature. Okay, and I know when you compute the derivative of this, there's one term involve how do I say involve this curvature, total curvature. You instead of compute minimize, you can compute the area for just a variation induced by family of these curves, but that's variation given by total curvature. But total curvature is bounded, so that's why you have this. Derivative is bounded, so this tells you the following things. If you have this estimate is doesn't matter. So this you only need to establish this estimate outside the small set, the set of very small measure, right? Because I say that if the 2 points, if 2 times are very close to each other, this is dominated by a difference. Okay, so that implies that you only establish that inequality on the open dense set. I mean, not open dense, an open set whose complement is sufficiently small. Okay, so this tells you only establish 2 suffice to prove 2 on an open set. Say V contain the 0 bar, 0, 1 bar, such that the complement, measure of complement is open. Is small. Okay. So here, of course, you also use the fact which I have no time to write now, because if you change your value slightly here, this is also continuous change. Okay. So you can just prove this inequality at the corresponding subintervals, then sum them up. Okay. So all of these bad things you can include here. Okay. So this is one thing. This is so. Last this step 4. So this is a key estimate. And so in the original paper, it's just say it can be proved, but it's it's actually it's a bit tricky too. It's not direct from existing literature. So let me say the following. So this is let curve be any solution of shrinking flow. Any solution of curve shrinking flow in say some interval. Okay, in some interval. So t prime, say, some interval t prime to t double prime. I don't know, of t1, say. So let's assume a length of this. So length of this so assume such that satisfying. So first, the length of this c of t prime, the initial one, is at least it's an r. Okay. So here there is a delta and some constant c1 tilde, ci tilde. Okay. So this is some r, and r less than 1. Okay, and also you want to assume this the total curvature of any things in the C prime, okay, any segment here, and such that the length of this is less equal to r. Okay, so then you look at the total curvature. So you want to say this is less equal to delta. Okay, less equal to delta. So then so delta is certainly t. You want delta r squared to be less equal to t1, so that the flow is defined. So then the curvature, you can bound the curvature. K squared is bounded by c0 prime, c0 over t minus t prime. Okay. You can also bound the derivative of maybe I just say you can also bound the derivative of h, the total curvature in the c1 tilde. And so on. Okay, so on. So maybe I just usually for mean curvature, once you bound the curvature, it's standard to bound all the other derivatives. So this theorem says if you have a curve in a curve shortening flow, if a total is not too short, okay, that's why the first case we rule out that. So in the first case appeared, it's not quite in the things we needed, but it's appeared because of this assumption here. Okay, so if this is sufficiently long, and also assume locally for each short section of this curve is almost like flat. Like total curvature is small, that means its variation is not too big. Okay. Then I want to say you can bound the curvature for up to certain time. So this is more like epsilon regularity estimate. Okay. So the things here is since I have this, so that will imply for any there's b, for any b, so this c of this open set of k squared will be bounded by b for a measure set of for V contained in this interval, and with a measure of a V bigger or equal to a T1 bar, T0 bar minus B inverse. Maybe up to some constant C3. Okay. So this condition is, so then you can think that you choose R small enough. So this condition is always true for this, because there I bound the K square. By Schwarz inequality, you can bound the total curvature on a small arc length, small section of curve for those T. And so this condition will be satisfied for those T. Okay. So once this is satisfied for those T, then I have a curvature bound. I have a curvature bound at certain time intervals. So as lambda goes to 0, I have a curvature uniformly bounded. This bound may depend on, the B may depend on initial this thing here, but it's okay. But independent of lambda here. Okay. So that means as lambda goes to 0, for this open set, this flow converge to mean curvature flow in the original sense. So you can apply the argument I used before to derive differential inequalities. And then what left is a small difference there. It's negligible. Okay. So now you say, okay, this this condition also here means if this is small. If it's small, you choose this to choose R so that it may depend on that things. If it's small at a certain time, then it's small at all the time because of length control. Different, the length at a different time only different by some exponential factor here. Okay. So first case, if it's true, then it's true for all the time. But if it's not true, then I can, if the first case is, if length is sufficiently big, at certain time, then I can use the second things to guarantee the convergence of this flow and a very large open set. So that I can apply the previous argument to get differential inequalities. Okay. So this proves maybe I should stop now. So this proves for any C, you can derive this. Yes? V does not depend on lambda because this is uniform. This has nothing to do with lambda. It only depends on length. This is the integration of this. Okay. So this does not depend on yeah, so once you have this, you can prove the things. And there is one more step. In the sense, this is because this is for apply this. I apply for every C, every curve here. So step 5C. So here again, there's a technical part which I don't have time to say now. So since we need to establish that for every C, so far I argumented for fixed C. So this is done. So this done for any fixed B. For any fixed B in S2, it's, the estimate is true. But you still need to do this for all the B uniformly. So how do I do that? It turns out you can bound, there is a bound which I write this down. So maybe I just maybe ask to reduce to a case, reduce the estimate for all B to a net of say BI sufficient dense a finite net in this such that any distance is small. So area is so the distance. So that how do I say? So such that the area. I have to specify. So maybe I skip that. So let's just talk a bit. It takes time. So in the end, what you want to do is giving two different curves. You can bound if two curves, initial curves are close to each other, then you want to bound you can bound the area which it bounds. Okay, it's like little annulus. And this when you deform these two curves along the mean curvature flow, and this area you want to control the area change of that. So that's again you can use it's basically dominated by change of the metric and ambient space, and you can just imitate what we did before to control that area. So then you can, in order, you don't need up to certain this small positive constant. What you need to do is you can just choose a finite set. You try to establish that estimate. Okay, so this net may depend on so the smaller Cassis, you might have the bigger this set might be. But anyway, in the end, you reduce finite many of them, then you run these arguments. Okay, to twist. So I already said once the proposition is proved, you can prove a Poincaré conjecture. You finish the proof. So I think I stop here. Thanks for.
Any questions? Final questions? So, thank you very much for this great series of talks. And, well, there is one more talk in the colloquium.
Yeah, so
you certainly will come back soon. So,
yeah. So for that one, we are below, I guess it's not, it's more like expository talk, and we are more emphasized on geometrization and some four-dimensional things.
So let's thank Tian again.